Hello again. This is the last of the videos. After this video, I'll see you on Wednesday morning at 8 a.m. sharp, and we'll have one-on-one time again. What we're going to do is finish up the lay chapter, the chapter from the lay book, and what we're going to talk about is something called the Cauchy Schwartz inequality. And then we're also going to apply Gram-Schmidt orthogonalization to a polynomial space using our new inner product. So we're going to extend the Pythagorean theorem to any vector space with an inner product. So if we have an inner product defined on a vector space, we have a norm. So we have two vectors, u and v, in this vector space. We have an inner product defined on it. So if I take the norm of u plus v and square it, remember the norm would be the square root of u plus v inner product with u plus v. But we're taking the square of that, so we skip the square root. When we use the properties of inner product, we can rewrite this inner product, u plus v inner product with u plus v, as the norm of u squared plus 2 times the inner product of u with v plus the norm of v squared. Because this is just going to be the inner product of u with u, this is the inner product of v with v, and then we have 2 of the inner products of u and v. So if the inner product with u and v is 0, that is, if these two vectors are orthogonal, then the norm of u plus v squared equals the norm of u squared plus the norm of v squared. That's just a generalization of the Pythagorean theorem that we're used to in R2. Okay, we're going to need that. What we're building up to is a proof of the Cauchy Schwartz inequality, which is given in your book. But there's steps missing, and I'm trying to fill in those steps. Consider the projection of v onto u. Consider the projection of v onto u, defined just like we did with dot products, as the inner product of u and v over the inner product of u with u times u. This is exactly how we defined it in R2 or R3 when we were just using dot products. And remember too that v minus the projection of v onto u is orthogonal to the projection of v on u. So remember, we had, when we're projecting onto a vector, when we were in the world of vector arrows, we said the projection of v onto u is the component of v in the direction of u. So now v minus the projection of v on u, the component along u, is the component, this component, perpendicular to u. Okay, so v minus the projection of v onto u is orthogonal to the projection of v onto u. Well, if they're orthogonal, we can use the Pythagorean theorem and say, well, the norm of v squared is definitely equal to this, because the projection of v onto u minus the projection of v onto u is 0. And then, since these two are orthogonal, we can use the Pythagorean theorem and divide them up like this. Therefore, the projection of v onto u must be less than or equal to the norm of v squared. So the norm of the projection of v onto u squared must be less than or equal to the norm of v squared. This you need in the proof that's presented in lay. Once you can say that, then you can say that, okay, in lay, he shows that the projection of V onto U would be that inner product of U and V squared over the norm of U squared. He goes through the algebra to show that. And then you can say that since that's the norm of the projection of V onto U squared, and we just showed that it was less than or equal to the norm of V squared, then this inequality follows. So the inner product of U with V is less than or equal to the norm of U times the norm of V. And this is a very famous inequality called the Cauchy Schwartz inequality. And actually, a lot of books now are saying the Cauchy, and then there's another name that begins with B, a Russian name, and I can't remember it, but they'll often say the CBS inequality. The Cauchy Schwartz inequality, because 3 mathematicians came up with it, were credited with it, but I think it was the Russian mathematician who was the first. And he's left out. That's pretty bad. Okay, so that's the Cauchy Schwartz inequality, and it's important that you go through that proof and understand that proof. I will ask you to reproduce it at some point on a test. Okay, last thing we're going to do with this inner product, we can do Gram-Schmidt orthogonalization. So let's say V is the set of all continuous functions from on the closed interval -2 to 2. And let's say we have a basis for a subspace of that space, 1t t squared. And our inner product is like that we've already defined for our function spaces, the integral from -2 to 2, f of t, g of t, dt. Okay, so how do you do the Gram-Schwartz or Gram-Schmidt orthogonalization? You let V1 be 1. V2 then is going to be the second basis element minus the projection of that second basis element onto V1. So you've got minus the inner product of V1t over V1 times V1. So now we have t minus, okay, so the inner product of V1 is 1 with t. It's the product of 1t, the integral from -2 to 2, t dt. The bottom is the integral of 1 times 1, which is 1 dt, from -2 to 2. So all that is just equal to t. Then to find the next element of the basis, the orthogonal basis, we take t squared. Notice that this was 0 here because we're integrating from -2 to 2, and our integral is going to be t squared over 2. So when you integrate from -2 to 2, you're just going to get 0. So that's why this just turned out to be t. So then the third would be t squared, the third component, minus the projection of t squared on V1 minus the projection of t squared on V2. So we've got inner products instead of dot products. So we do the calculus, and we should get t squared minus 4/3. Once again, I want to do the inner product of V2 and t squared. V2 is t. T times t squared is t cubed. Our integral is going to be t to the 4th over 4. So from -2 to 2, that's going to be 0. That's why that drops out. And here we're left with 16/3 over 4. So our end result is t squared minus 4/3. So we took this basis for a subspace of this vector space, and we made it into a set of orthogonal vectors with respect to this inner product. And you can check this. Check the inner product of every pair of these and you'll get 0. Okay, so you have homework and you have something to send me. You have to send me work on a problem similar to this. And I swear I'm going to catch up with the grading. And I'll see you Wednesday morning. Bye.